Welcome back to the Deep Dive. We're continuing our exploration of mathematics today, and we're tackling a real giant.
We certainly are.
Goldbach's conjecture. Just the name sounds significant.
It is. It's one of those problems that's, well, deceptively simple to state.
Right. So remind us, every even number greater than 2
Is the sum of two prime numbers. That's the essence of it.
simple enough, like 4 is 2 plus 2.
Exactly. Or 6 is 3 plus 3, 8 is 3 plus 5, 10 could be 3 plus 7, or 5 plus 5. It just keeps working.
And it's been around for, what, over 250 years?
That's right. Mid-18th century, and despite everyone assuming it's true.
And computers checking it up to absolutely astronomical numbers. I saw something like 4 times 10 to the 18.
An incredible number, yes. Verified that far. But still no formal proof. It remains one of the big unsolved problems.
So that's our mission for this deep dive.
Yeah.
Try and understand why. Why is this simple-sounding idea so incredibly hard to prove? What's the holdup?
Well, the difficulty really lies deep down in the nature of the numbers themselves. You're trying to connect addition, how even numbers are defined, basically with multiplication, which is fundamental to what a prime number is.
Okay, say more about that. Addition versus multiplication.
Primes are all about divisibility, about multiplication. They only have two factors, one in themselves. Even numbers are just multiples of 2. They belong to the world of addition and subtraction in a sense.
So the conjecture forces us to build a bridge between these two kind of separate worlds of number theory.
That's a great way to put it. A proof would need to somehow link the additive structure of even integers to the multiplicative structure that defines primes. And that link, well, it's proven extremely elusive.
It doesn't seem obvious how you'd even start building that bridge mathematically.
Precisely. It hints that maybe our current tools aren't quite right, or we're missing a fundamental insight into how these two aspects of numbers relate.
Okay, but given that it seems true, and the computer checks, there must be some strong reasons beyond just examples to believe it holds right, some mathematical intuition.
Oh, absolutely. There are strong heuristic arguments. Think about probability. It relies on ideas related to how primes are distributed.
Like how often they pop up.
Sort of. We can use techniques inspired by sieves, like the old sieve of Eratosthenes, for finding primes.
Right, where you cross out multiples.
Yeah. Here, the idea is a bit different. It's more about looking at how primes spread out when you group numbers by their remainders after division modular arithmetic.
Okay. Like primes modulo 3 or modulo 5.
Exactly. There's a powerful result, the prime number theorem for arithmetic progressions, which basically says primes don't bunch up too much. They tend to be distributed fairly evenly across the possible remainders, as long as there isn't an obvious reason for them not to be.
And the regular prime number theorem gives us a handle on how many primes there are overall, roughly x over log x.
That's the one. It gives us the density.
Yeah.
So combine that density with the idea that they're spread out.
Then as you look at larger and larger even numbers, you just have more and more primes available to choose from.
Precisely. And more potential pairs that could sum up to your target even number.
So the chances of finding an even number that can't be formed by summing 2 primes seem to shrink dramatically as the number gets bigger.
Statistically, yes. It becomes incredibly unlikely. There's even a visual plot called Goldbach's comet.
A comet?
Yeah, it plots even numbers against the number of ways they can be written as a sum of 2 primes. It tends to show this thickening band more ways for larger numbers. It looks a bit like a comet's tail sort of broadening out.
Huh. That's a neat visual. But, okay, you keep saying heuristic, statistically unlikely. It's not a proof.
No, definitely not a proof. It's strong supporting evidence, strong intuition, but it doesn't rule out some, bizarre counterexample lurking way out there or some subtle structural reason we're missing.
So what are the actual roadblocks for a proof? You mentioned our tools might not be right.
Well, some of our best tools for additive problems, like the circle method, which was brilliantly used for the ternary Goldbach problem.
The sum of 3 primes. We'll get to that.
Right. That method works better when you have more variables, like 3 primes summing to an odd number. With just 2 primes summing to an even number, the analysis gets much harder. Some of the error terms are just more difficult to control.
Fewer variables makes it harder. That sounds a bit counterintuitive.
It does, but mathematically, sometimes having more terms allows for more cancellations or averaging effects that simplify things. With just 2 primes, it's a bit too rigid, in a way, for the method to grasp fully.
Okay. And I read about something called the parity problem. That sounds mysterious.
Ah, yes. The parity problem is a known limitation of many sieve methods. Put simply, these methods are often good at distinguishing between numbers with an odd number of prime factors versus an even number of prime factors, but they struggle to distinguish between, say, numbers with 0 prime factors, like 1, and numbers with an even number of prime factors greater than 0.
And since primes themselves have one prime factor.
Well, primes are the fundamental building blocks. The issue is that sieves often can't easily guarantee that the number they find is a prime with one factor, rather than a product of, say, 2 primes or 4 primes. They can often guarantee it's not a product of 3 or 5, but pinning down exactly 1 is the hard part related to parity. Goldbach needs exactly 2 primes.
So our sieving tools have this kind of built-in fuzziness when it comes to even versus odd numbers of factors.
In a manner of speaking, yes. It's a fundamental barrier that's prevented sieve methods alone from cracking Goldbach. It's why results often involve almost primes.
Right, it feels like we keep bumping into this fundamental split addition versus multiplication, even versus odd.
Exactly. Donald Knuth apparently felt it's likely true simply because there are so many ways to write an even number as a sum of 2 odds, it seems inevitable some pair must be prime. But that sheer number of possibilities doesn't overcome the clash between the additive structure, sum of 2 things, and the multiplicative definition of prime.
It's a fascinating tension. Now, you mentioned the ternary-Goldbach conjecture.
Yes, the weak Goldbach conjecture. Every odd integer greater than 5 is the sum of 3 primes.
And that is proven.
Yes, finally proven rigorously by Harold Helfgott in 2013, a major achievement. It built on decades of prior work, of course.
And interestingly, if the main conjecture, the binary one we're discussing, were true.
The ternary one would follow quite easily, so proving the binary conjecture would automatically prove the weak one again.
So the stronger version implies the weaker one, but proving the weaker one didn't directly solve the stronger one.
Correct. It provided techniques and insights, but the 2 prime case remains distinct.
What about other progress? Have people managed to chip away at it in other ways? You mentioned almost primes.
Yes, that's a very important line of attack. Chen Jingrun's theorem from the 70s was huge.
What did Chen show?
He proved that every sufficiently large, even integer can be written as the sum of a prime, and a number that is either a prime or a product of 2 primes, sometimes called a p plus pure result.
P plus P2. So 1 prime plus a number that has, at most, 2 prime factors.
Exactly. So incredibly close. Just need to guarantee that second number is always p, not p.
Wow, that feels tantalizingly close. It's like you're right at the finish line.
It does feel that way. Another approach is to study the exceptions. If Goldbach isn't true, there must be some even numbers that cannot be written as the sum of 2 primes. We call this the exceptional set.
Okay, so can we prove that this set is small, or maybe even empty?
Proving it's empty is proving the conjecture, but mathematicians have shown that the set, if it exists, must be very sparse. The proportion of even numbers up to x that might be exceptions gets smaller and smaller as x grows.
So exceptions would be incredibly rare.
Extremely rare, and under assumptions like the generalized Riemann hypothesis, another famous unproven idea, we can get even stronger bounds on how rare they must be. Showing the set is finite or even empty without assuming GRH is still an open problem, though.
Right. Relying on another unproven hypothesis isn't quite the same.
No, but it shows how these deep problems in number theory are often interconnected. There's also Linux theorem related to this.
What does that say?
Linux showed that every large enough even number is the sum of 2 primes plus a bounded number of powers of 2. So n equals PO plus 2k plus 70k plus 2k, where c is some fixed constant.
Adding powers of 2 helps bridge the gap.
It seems to provide enough flexibility, and work since Linux has reduced that constant c significantly, getting closer to just the 2 primes. Again, chipping away, getting closer.
It's really incredible. All these different angles, sieves, circle method, almost primes, exceptional sets adding powers of 2, all converging on this one problem.
It shows the depth and richness of it. It sits right at this crucial intersection of addition and multiplication in the integers.
A structure we think we understand, the basic whole numbers, still holds these profound mysteries.
Absolutely. And the fact that Goldbach remains unsolved after so much effort and progress elsewhere in number theory just highlights that there's likely something fundamental about this additive multiplicative relationship we haven't grasped yet.
So as we wrap up, it leaves you wondering, doesn't it? Is the proof just fiendishly complex, requiring tools we haven't invented? Or is there some, I don't know, elegant, simple insight hiding in plain sight that unlocks the whole thing?
That's the million-dollar question, isn't it? Or perhaps the Clay Millennium Prize question, if it were one. Is it a fundamental limitation, or are we just missing the key? The evidence suggests truth, but the proof. The proof remains elusive.
A perfect example of how a simple question can lead to the deepest mathematical waters. Thank you. This has been truly illuminating.
My pleasure. It's always fascinating to talk about Goldbach.